Hello everyone, and welcome to the next part of the lecture, which is devoted to spin transit torque and spin pumping phenomena. When we speak about spin transit torque, we usually refer to this kind of picture, which consists of two ferromagnetic layers, ferromagnetic layer 1 and ferromagnetic layer 2, separated by a spacer of normal metal, non-magnetic metal. And we know already from the previous lectures what happens if you have such bilayer structure of one ferromagnet and normal metal, and when we send electric current through it. So when electrons are coming into ferromagnetic layer, they become spin polarized because we have here different density of spin up and spin down electrons at the Fermi level. And then this spin polarized current is injected into the normal metal layer. And we also know that the spin polarized current will propagate only a certain distance, named spin diffusion length. And if you are taking point already large and far away than from the interface as spin diffusion length, then most likely there was a spin flip scattering event, and it means that your spin polarization disappears. Therefore, in the structure, when we study spin transit torque, we are using thickness of a spacer to be smaller than the spin diffusion length, because what we want to have this current to reach in the spin polarized form to reach the second ferromagnetic layer. And what happens when it reaches the second layer? There is a spin angular momentum associated with the spin polarized current, which is then induced in the second ferromagnetic layer. And if the orientation of magnetization in the ferromagnetic layer 1 is not equal to the orientation of magnetization in the ferromagnetic layer 2, like is shown in this figure, then this spin polarized current will create torque acting on this magnetization. And in the very simplest words, this current tries to put this magnetization to point in the same direction like the original magnetization which created the spin polarization. So where do we see spin transit torque in our experiments, and in which cases we use it? I would say there are different manifestations of STT, but I would define three as the most commonly used. First of all, if you have such situation and you send current, then you can really, it's efficient effect, you can really switch magnetization of this layer to point in the same direction like it was, like this layer is. So for example, you have such a situation when two ferromagnetic layers are pointing in the opposite directions, and then when you send current through it, you can switch magnetization of this magnet to point into the same direction as the original one. So it means that you can use it for switching of magnetization, and obviously it means that you can use it for data storage. And this is something which is used in spin transit torque magnetic random access memory, MRAM, here. Second situation in which we meet STT is a motion of the main wall with electric current. So imagine that instead of having this complex heterostructure, you have just a normal ferromagnet, but there is a domain wall inside. That means that from one side of the main wall, you in one domain you will have magnetization pointing in one direction, and from another side of the main wall you will have magnetization pointing in the opposite direction usually. And it means that sending current, we can get very similar physics, but instead of switching magnetization directly, like in this case, what will happen, there will be a motion of the main wall, which is triggered by spin transit torque. And there is a certain manifestation of this phenomenon. It's related to the excitation of magnetization precession. It means that if you have such system, and usually when, for example, current is smaller or so, and then you induce spin transit torque into your second layer, and if torque is not strong enough to switch magnetization, then what happens, you will get magnetization precession of this magnetic moment, with a given frequency, and then you can use this, for example, as a micro SO. So you have some DC current and you will get micro irradiations. Okay, so that was a general overview of spin transit torque effect. So we know what to expect from today's lecture. And now let us move step by step to get a better understanding of this work and how it is described. So here you see the same structure, a picture taken from Krishna. So there are two magnetic layers with different magnetization orientation, separated by non-magnetic spacer. And as the current of S electrons in the normal metal flows with equal polarization of spin up and spin down electrons, when it passes through ferromagnetic media, so this one, it's getting partially spin polarized. So all the details we know about the spin polarization, and now you can define the spin transit torque phenomenon in the following way. In magnetic materials, the electron current is spin polarized, and the transfer of their spin angular momentum leads to the spin transit torque here in the second magnetic layer. What we need to keep in mind that in this case, the flow of spin angular momentum through the sample shouldn't be constant. We, in some sense, need to have source and a sink of spin angular momentum, and this can be realized in two ways, which we already briefly discussed. The first one you see here. We just need to create such a structure consisting of two magnetic layers whose magnetic moments are not collinear, and then one acts as a spin filter and injects the spin polarized current into the second. And another way how you can realize this is a domain wall. So the spin angular momentum of the spin polarized electron can change as it rotates to follow the local magnetization. Yes, so we use the same magnetic structure, but with complex distribution of magnetization, and then this current is moving and polarization just follows the domain wall. Okay, let us introduce now parameters with which we are working. So what are these indexes? T large stays here for thick ferromagnetic layer. Why it should be thick? The idea is that we want to create such situation that one magnetization of this layer is fixed, so we cannot change it when we send current in one or another direction. So we want to have it really like a spin polarizer and to stay in the same configuration always. And the easiest way how you can do it to just make it thick, and then it will be stable there. And then we have here N material, which stays for normal metal spacer, as we discussed. And T small stays for thin magnetic layer. Again, why thin? Because this magnetic layer, as opposite to the thick one, we want to have flexible. We want to have, it's usually named a free magnetic layer, in the terms that it's relatively easy to change its magnetization orientation in one or another direction. And that's exactly what we want to do with our spin transit torque. Then on top we have to define thicknesses. So there is a delta N, so thickness of spacer, thickness of thin material, and thickness of thick material. And as we discussed, so principally we want to have all these three thicknesses to be smaller than the spin diffusion length, as we discussed in previous lecture. Okay, and what actually happens when we inject the spin polarized current, which propagates our spacer and enters a thin ferromagnetic layer, then principally as the exchange interaction with this layer is trying to align the spin momentum of conducting electrons once again along the magnetization direction of Ft capital. So that's what is going on here, and since the total angular momentum has to be conserved, the transverse component has to be transferred to MT. So it means that you split this magnetization into two components, and one of these components is transferred into the next magnetic layer, and the repolarization of the current Ft gives rise to the effective torque. Yeah, so that's why it's named spin transit torque. because at the end of the day we will get this torque which is acting on MT small. And this torque aligns MT towards the direction of polarization of the incoming conducting electron, and thus towards the MT capital. Okay, so this is the idea. It's all about the conservation of total angular momentum, and this is the physics which is staying behind the spin transfer torque. Okay, how we can describe this torque? Tau, and here I would like to give credit to the people who discovered it and have written it for the first time. It's Professor Slanchevsky and Professor Berger. I suppose Professor Slanchevsky was slightly published his paper slightly earlier, therefore this spin transfer torque pretty often is named simply as a Slanchevsky torque. But these are two papers which appear practically simultaneously. And how this STT term looks like is shown here. So you see that it is first of all proportional to the current which we sense through our structure. You see in there that it depends on the saturation magnetization of your magnetic layers. It depends on the thickness of the layers. So for T, and you need to, so you can get torque of course in both layers. Therefore T small stays, just need to write it separately. Then you use always T small, or you can write this torque for T large, then you just put T large here. And here you see this all interesting parameter epsilon, which is just efficiency factor that accounts for the various details such as the polarization of the ferromagnet and the band structure and any mismatch at the interface. As I said, the interface is always very important in all these experiments, and all this information is sitting using this epsilon. This is Planck constant, this is charge of electron, and the most important part is this one. So you see that you have two cross products. Here's the cross product between thin and thick layer, and here again you have 1m depending which torque do you need for thin or for thick layer. So that's it, and what you immediately can get is that understanding that in general the non-collinear geometry with a finite angle between the moments is required to see any spin torque effects. So it means that if you have anti-parallel magnetization like this, strictly speaking, you shouldn't get any spin transfer torque according to this formula, but we should not forget that in all real situations, we always have some semi-fluctuations of magnetization, and therefore if you apply current even in this anti-parallel states, one little fluctuation is sufficient just to start the switching process, and then it will be enhanced, and torque will be maximized, and then you will get switch of the magnetization like you need. How to realize it experimentally, and how large should be your current. So current here should be rather large. Density of current 10 to the power 7 or 10 to the power 9 ampere per centimeter squared. Nevertheless, in this case, the spin transfer torque effect is quite efficient. So there are two typical configurations which people use to study STT. They are shown here in these two pictures. And the first one, it's a point contact geometry made mechanically or through a microfabrication. So it means that you have such a layer of hard magnetic material, so fixed layer, thick, then a spacer, and then you have thin magnetic layer where you want to change magnetization, and then you can just create mechanically such a nano contact. And it should be very small diameter, let's say smaller than 200 nanometers. And the reason is that you want to achieve this high current density. So you don't want to send 1000 amperes through a structure, but if your diameter is order of 100 nanometers, then the real current which you send through the structure is of order of 1 milliamp. This is something you can easily work with. And then when you send current with such high density here, you can switch polarization of the layer. So this is one way to go, but there is another way which is more commonly used. It's that when you have such a stack, already with a size of 10 nanometer, 100 nanometers, like here, and then you can create it with lithography methods, some etching, or some drawings, etc. It's a very serious piece of technology staying behind, but people learn how to draw it nowadays with high efficiency, that interfaces are good, and that the size is very small. And what is the difference between these two methods? Principally here, in order to switch magnetization, you need around 2 orders of magnitude smaller current. So this 10 to the power of 7 stays mainly for this case, and the 9 stays for this point contact case. And the reason is very simple, because if you want to switch magnetization orientation of this layer, you see it's free here, the edges. So it's not coupled to anything, and you can do it relatively easy. If you want to switch magnetization of this, some part here, then of course you need to do something with exchange interaction at the edges of this region, which wants to keep your magnetization parallel. So you need 2 orders of magnitude more current in order to break also this exchange interaction to create here domains. A few words about current direction. So we have discussed situation when we send currents through fixed ferromagnetic layer, and it's coming to thin free layer, and then spin polarization is switching magnetization to the direction like it was like a fixed part. So it means that this is this part of our picture. It means here we have, this is some scale. For example, this is just resistance, but we will come to this in the next lectures. But imagine that this is a measure for magnetization of your magnetic free layer in one direction. If you have magnetization pointing in this direction, then you have this resistance. If you have it in opposite direction, right, then you will get higher resistance. So this is just gives you information about magnetization orientation. And then you have originally this state, and you start to apply current in one polarity. And what happens if your current is large enough, your torque term is proportional to current, so at some point you will reach high enough, you will apply large enough torque in order to switch magnetization. And then further increase in current changes nothing. But let us look what happens if you then decrease current to this point. Then magnetization, these 2 layers are just parallel magnetized, and that's it, like it's shown here. You know? They're parallel magnetized and everything's fine. But what happens if you send current in the opposite direction? You change the direction of current. Then situation will be symmetrical, because for a certain time you will start again to apply torque on the system, on the free layer, and for some time you will change nothing, but at some moment you will get switch of magnetization back to this case. So it means when you change polarity of the current, you change the sign of the torque applied. So in one case, when you send current like here, you want to keep magnetization parallel, but if you send now current from right to the left, you want to have these 2 magnetic layers anti-parallel. It maybe looks a bit weird, but it's rather easy to understand, because what you should take into account also a reflection of electrons. So when you send current here, you of course will get some small spin polarization of the electrons, but assume that since the thickness is very small, spin polarization is small. Then what happens, this thick layer acts as a filter, and it means from all different spin polarizations, the electrons which have proper polarization, like this magnetization, will go through, but the rest electrons will be reflected. And if they are reflected, it means that you have kind of spin polarized current flowing again into the free layer from this side, but it will have spin polarization just opposite to the polarization of the fixed layer. Therefore, sending current in this direction, it's analog of sending spin polarized current in this direction, but with inverted spin polarization. And that is the reason why we can switch our magnetization in one or another direction, just switching the direction of the current. This is very important for memory. And the last ingredient, as I told you, of the spin transfer torque is possibility to excite magnetization precession. To explain what does it mean, I need to show you this animation made by Dmitry Bashkov, and he was a PhD student in Kaiserslautern, so now he's professor in Colorado Springs. And what will be shown now in this animation, you can see here, and this is nothing else, it's so-called Landau Lifshitz Gilbert equation. Here you see it describes the variation of the magnetization shown here with red arrow, with M, as a function of time, as a function of magnetization itself and applied external field. H effective, usually you have different contributions to this H effective, but in the simplest case, you can consider only bias in external field, H0, which will be here. And then what you can see in the animation is that when you will create such angle between applied field and M, H is kind of pulling M again back. As we know already, magnetization prefers to stay along the applied magnetic field in ferromagnetic structures. But the Landau Lifshitz torque equation tells us that this will not what happened, because you see here a cross product, and exactly like you have mechanical spinning top, you know when it's precessing. So first you make your top rotating, it rotates vertically and it just stays, nothing happens. But at some moment when it's losing its kinetic energy, it starts to flow down. And in this moment, your mg force starts to act. And this mg force wants to put it simply down. But instead, because it's rotating, you will get a torque which is pointing perpendicular to both to mg and to your axis of your top, perpendicular to this direction, and you will get a mechanical precession. This is something which is used in gyroscope and so on. That's what you know from mechanics. And exactly this same situation happens here, but instead of spinning top, we have now magnetic moment M, and instead of mg, which would pull this down, we have this H, which wants to put it back. And this is something which is described by Landau Lifshitz equation, because in this case, you will get this torque, again pointing perpendicular to both of these vectors, and because of this torque, you will get magnetization precession. And the next point, of course, as soon as you have excited magnetization precession in your system, you always have losses. So at the end of the day, energy always goes to phonon system, to temperature. And the same happens with magnetization here. It will not precess there forever, and you need to find a way how to describe this damping. There are different mechanisms how we can describe damping, but usually we use so-called Gilbert damping term, which we see here. And here C alpha is a Gilbert damping parameter. So it's a parameter which shows you how fast your precession will disappear. So how large is your damping, let's say. In physical meaning of alpha, in the simplest case, you can say that 1 over alpha gives you the number of precession before it disappears. For example, we were discussing permalloy, and permalloy has around 10 to the power minus 2 damping, so it means that after you excited precession, there will be 100 periods before it will disappear, over before it will decrease its amplitude of precession to 1 over E value. If you are speaking about yttrium iron garnet, which is a material which ensures its smallest damping nowadays, then you speak about 10 to the power minus 4 and sometimes 10 to the power minus 5. So it means that you will have around 10,000 and more precessions after you excite magnetization precession. But it doesn't change the physics. The physics is always the same, that as soon as you have this Gilbert damping term, which is empirical formula and just describes viscous damping, then you will get precession moving in this direction. So it will draw some spiral because the length of M should be conserved in this model. And now when you have this equation, LLG, you just add here additional Slanchevsky torque, describing your torque, and principally you can get all physical phenomena which we were discussing is only little comment here that you need to distinguish between two cases when you describe two magnetic layers separated by a spacer, and when you describe magnetization which is special non-uniform, namely when you're working with domain wall. So in domain wall, you need to make one step further and to split this term into two parts, adiabatic and non-adiabatic. One conserves an angular momentum, and in the non-adiabatic term, it might arise from linear momentum transfer, spin slip scatter, and spin relaxation. So this is one step deeper, but just keep in mind that when you want to describe these two situations, you might need to modify your model a bit. And we are coming to this slide, which principally describes you the physics of what we expect. So this is our magnetization precession, and this is a damping term, Gilbert damping term, which just tries to decrease precession angle, and that after some time we have no more precession. And this is the torque, spin transfer torque. And this spin transfer torque then can point in different directions, because as we discussed, depending on the current direction, you can have positive or negative spin transfer torque. That means that you can speak about different situations, and imagine that you apply the torque in a way that spin transfer torque is pointing simply in the same direction as damping. Then what happens when you excited your magnetization precession, then you applied current and you applied negative spin transfer torque, it means that it simply increases damping of your system. So in the free layer, other than the damping being accelerated. So it means that you just enhance damping in your system, and that's what you see from spin transfer torque. Of course, it's much more interesting that when you have opposite current polarity, like is shown here, the damping and spin transfer torque are pointing in the opposite direction. So then you can have principally two qualitative scenarios. In the first scenario, you can reach such situation that damping and spin transfer torque are compensated. For example, if the damping torque increases with precession angle theta faster than the spin torque, then MT may achieve equilibrium precession at some fixed angle. So it means that you, of course, in order to give equilibrium, you need to have different dependencies for the torques, different dependencies on the angle of precession, but pretty often in experiment you have such situations that you just apply spin transfer torque positive, you increase angle of precession, and then you will reach some equilibrium. And what happens afterwards, you will get some magnetization precession. And principally the device, which is very popular, intensively studied now and over the last 10 years or so, is spin transfer torque nano-oscillator, STNO, and the idea is that people want to create micro-resource. The main problem here is that it works, but the power of this micro-irradiation is still not large enough because we need micro-sources everywhere. Yeah? So our Wi-Fi works because our mobile works, smartphone and microwave is everywhere. And of course, if you want to have simple, reliable micro-resources that you just apply battery, you use DC current and you will get generator shown at 2 gigahertz frequency, for example. That's everything what is needed. But there are several problems. First of all, the line width of this STT sources, it should be as narrow as possible, tunability, but the largest problem is of course power. Therefore, what people are doing now, they're trying to put many of these nano-oscillators and to synchronize them. And then if they synchronize, you can multiple power and you should be able to get the values which you need for industry. And the spin transfer torque nano-oscillators, it's a one way to go, and another way to go is to use spin Hall effect, as we know. When you put two magnetic layer and then on top you put platinum, and then instead of sending current through your material, you can send current along platinum. Then, as we know from spinfoil effect, it will create spin polarized current transfers to the surface, and you will induce spin polarized current into this layer. And this will be exactly your spin transit torque. So nowadays, this combination of spinfoil effect with spin transit torque is named usually spin orbit torque. And this seems to be very interesting, particularly the group of Johann Ackermann has shown synchronization of many spinfoil nano-oscillators, and they have really great progress in the parameter characteristics of these microwave sources over the last years. Good, so this is what we have in this case. This is when you need microwave source, but in some cases you need, or even more popular, you need to store data. So it means that you don't want to excite magnetization per session, but vice versa, you just want to flip it. You apply current, you flip it in one direction and another direction. This is technology which is used in a magnetic random access memory, and usually this precession and switch of magnetization are coupled. So how it usually happens is that you just apply much larger torque than in this case, and then after a few periods, your magnetization will just flip to the opposite direction, and then you can switch magnetization. And this is something that is used for storage data. I do not speak in this lecture about motion of domain walls with current, but to compensate this, I will show you this nice video about racetrack memory. So here is Stuart Parkin. He's really unique, very, very interesting person for communication. I always happy to talk to him at conferences and so on. And he has proposed the idea of racetrack memory, which particularly relies on the fact that we can move domain walls in our system with using spin transit torque. So let us simply see how it works.
This is Cameron Chai from azonano.com, and today I'm speaking to Dr. Stuart Parkin, who's an IBM fellow. He works at the IBM Almaden Research Labs, and he's an experimental physicist, and of note, he's a pioneer in the area of spintronics. He and his team have already developed a radical technology that enormously increases the storage density of hard disk drives, and today he's in Sydney at the ICON 2010 conference to talk about racetrack memory. How are you today, Stuart?
Very good, thank you.
Good to hear. So what is racetrack memory?
Racetrack memory is a new type of technology that we're developing based on some fundamental new concepts in the area of spintronics. What racetrack memory will enable us to do is essentially to completely replace magnetic disk drives with a solid state technology without any moving parts. So we'll be more reliable, and we'll use less energy, and will be much faster, 1,000,000 times faster, to access the first bit of data than is possible today in magnetic disk drives. But in addition, racetrack memory could also replace very many forms of solid state memory. So computers today are rather complicated because they need a whole hierarchy of different means of storing digital data, ranging from magnetic disk drives, which is a great technology, provides an incredibly cheap means of storing digital data, but it has a few drawbacks. It's a little bit unreliable, and it's extremely slow. And at the same time then, racetrack memory in computers, you have solid state memories where you trade off essentially cost and performance. So a complicated hierarchy of memories. What we want to do with racetrack memory is provide a new type of memory that would be, if we would like to call it a storage class memory. It will have the enormous storage capacity of a magnetic disk drive at roughly the same low cost, but it will have the very high access, very rapid access time for reading and writing of conventional solid state memory, and the same high reliability of solid state memory. That's what we plan to do.
Right. And how does it actually work? I hear analogies between racetracks and race cars and things like that, and that's obviously where the name came from, but how does it actually work?
Well, okay, the name of racetrack is because it's really a very different in structure from nearly all conventional memories, solid state memories. And what we want to do, the reason for we call it racetrack, is that we're going to have magnetic nanowires, and the nanowires will contain magnetic regions, like little race cars. And the race cars, we're going to move these race cars up and down these nanowires, which will stand above a silicon wafer. And so in sort of the same area of silicon where today we store a single bit in a conventional solid-state memory, we can store many, many, many bits by storing them out of the plane of the silicon wafer into the third dimension in these very, very tall magnetic nanowires. So the concept is the data sort of exists like in these tree trunks, and you bring the information down, you race it down to the surface of the silicon wafer, where we'll have means of detecting and writing that information into the nanowires. And then we'll race the information back into the forest, into the tree trunks when we no longer need it. That's the idea. So we can shift the information up and down these trunks, if you like, these nanowires, and then just read it in the surface of the silicon wafer. So each racetrack will have a single reading and writing device, but it'll be entirely different from disk drives. There's no moving parts, no moving atoms. It's simply magnetic moments that will be reorienting, which gives it its fundamental advantages of high reliability.
And how much faster do you expect it to be than current technologies?
Okay, so we have to again compare current technologies. Means that in a typical computing system, a lot of the data will be stored in disk drives, but the disk drives are so slow that in order to carry out computations, you really have to take the data and put it into a solid-state memory where you can operate on the data more quickly. So we'll be much faster than disk drives. We are about 1 million times faster to access the first bit of data. Compared to conventional memory, we'll be on the side of the very, very fast memory, not as fast as the very fastest memory, which is static random access memory, but that's a super duper expensive memory as well. So we'll be very, very cheap, about the same cost as a disk drive, and therefore about 100 times cheaper than most conventional solid-state memories. So it's very, very cheap, but high performance.
So it'll be excellent for things like portable computers and like mobile electronic devices, that type of thing?
Certainly. In fact, it will be fantastic for all computing systems, including mobile and non-mobile applications, but mobile in particular will be very useful, because if you have a laptop with a disk drive and you have to rotate this glass disk, it's a very large object, it takes a lot of energy to accelerate it to the speeds at which you need to rotate it to get even the modest access times that are possible today. So with racetrack memory, because we're not moving any atoms or any parts, we're going to use much less energy. So for portable applications, and generally speaking, when we're in an environment in which we wish to reduce energy consumption, and we will use much less energy in the racetrack memory than compared to magnetic disk drives.
And approximately how far off do you think racetrack memory is from hitting the marketplace and being found in typical consumer items?
Well, racetrack memory, so turns out I first proposed this concept about 5 years ago, and in the last 5 years we've demonstrated the fundamental materials and the physics, which is entirely new. So work. So maybe as an aside, let me mention that the physics is that of spintronics. Spintronics is the idea that we can create entirely new materials and devices by controlling the flow not of electrical charge, but the flow of electrons whose spins are oriented in the same direction, parallel to one another. And by flowing currents of electrons whose spins are oriented in the same direction, they're so-called spin polarized, we can use those currents in a variety of ways. So in the past, you mentioned at the beginning, we had a big impact on magnetic disk drives. So I and my colleagues invented a technology involving materials which we nano-engineered on the nanotechnology scale, and by creating sandwiches of magnetic layers separated by non-magnetic regions, we could create extremely sensitive detectors of magnetic fields, where the property of the device is essentially that of the manipulation of spin polarized currents. So back to your question so now we've demonstrated in the last 2 or 3 years the basic physics works. We could use these spin polarized currents in a very different way from these sensing devices we developed for magnetic disk drives. We can use the current of spin polarized electrons, which actually corresponds to a current of spin angular momentum. We can use that current to manipulate magnetic regions in these racetracks, in these forest of tree trunks. That's how we're going to shift this information up and down the tree trunks using nanosecond long pulses of spin polarized current. So we know that it works. So what we need to do now is build a real prototype where we integrate in a single racetrack the reading and writing devices, and demonstrate that's possible. We estimate that will take in the region of 3 to 4 years. And then beyond that, maybe another 2 or 3 years to develop manufacturable prototypes, maybe arrays of these racetracks. So sort of generally speaking, it's in the range of 5 to 7 or 8 years out before it might come into the marketplace.
All right then, well, for everybody out there, I think we should all keep an eye out for racetrack memory, and hopefully we will be seeing it in our electronic devices in the not too distant future.
I hope so.
All right, thanks very much for your time, Stuart, and
Thank you.
Enjoy your rest of the time in Australia.
I'm sure I will. Thank you very much.
So much about the racetrack memory. So you understood that the main idea is that it's possible to shift here the domains with current, simply due to spin transit torque, as we just discussed, and then you can code the data into logic 1 or 0. The technology is very interesting, so Steve Parkin now is head of Max Planck Institute, where they continue this development. Nevertheless, you need also to understand that there are many obstacles on this way. So first of all, to fabricate simply the 3D structure, it's on its own is a very serious technological task. And I don't know, maybe simply technology is not ready for this. Also, it's extremely advanced over the last 10 years. Besides, you understand that you need to have this motion very fast, so you need to increase speed of motion, you need to increase stability of the manual. So this is a very, very serious task, and the progress which they made is amazing to my personal taste, because when I see the last talks of third parties, they use already artificial antiferromagnets, they add spin orbit interactions, they add so many different structures. So now there is a huge progress in this research direction, and nevertheless, as far as I know, it's not yet reached the level of industrialization. So just have a look how it goes further. Now I would like to switch to the next topic, which is spin pumping. So here you see the picture of spin transit torque. When you, for example, have such a system, imagine that here, the only difference is that what we've had is that this ferromagnetic metal now is replaced with ferromagnetic insulators. Yeah, so there is no real physical difference between if it's insulator or it is metal, but I just took this picture from this book chapter, and it's described on insulators. Maybe it's a bit easier to explain the idea. And this is the interface between magnetic insulator and normal metal. Then when you will send spin polarized current, you see here that there is, you send, let's say, spin down electrons into the surface. Then here you will induce spin transit torque, which might excite magnetization precession, as we discussed. So it means that reflected current will have different spin polarization, and you give the spin angular momentum into your magnetic system, and you excite magnetization precession, or in some cases you can speak about propagating spin waves and their quantum magnons, like it's shown here. But this all we discussed. So you have DC current, you excite RF magnetization precession. Spin pumping is a fact which is just opposite. What you can have, you just take the same structure, but instead of sending current, you first excite magnetization precession. So the easiest way to excite magnetization precession is to apply microwave signal at 10 gigahertz frequency, for example. Apply this signal into this sample into a microwave signal to this antenna. You excite magnetization precession. And then as soon as you have metal on top of your normal metal, on top of your ferromagnetic insulator, ferromagnetic metal, then you will induce spin polarized current, which propagates from this interface away from it. So this is, we mentioned briefly it when we were discussing about spin injection. So this is just one more mechanism how we can create spin polarized current, spin injection, but without using any DC current. So here you just need microwave signal, which excites precession, and then you induce spin polarized current flowing in this direction. And here I would like again to show you the pioneer publication where spin pumping was reported for the first time. So it was Jaroslav Terkovniak, Arne Bratash, and Gerrit Bauer. All are very active scientists. Since that time, they have published many new discoveries which trigger many research directions in the field of spintronics. And now I would like to speak about the combination of spin pumping with inverse spin Hall effect. So this experiment was done for the first time by Professor Eiji Saito, who is now at Tokyo University. He discovered inverse spin Hall effect and many other effects, which we'll discuss also in the next lectures. And the idea is quite simple. So we need to have combination of ferromagnetic layer, insulator, or metal, doesn't really matter, with metal here. And then since we want to start with spin pumping, what we do, we apply microwave signal, RF signal at 7 gigahertz, for example, and we excite magnetization precession here. As soon as you have magnetization precession, as you know already, you will inject spin polarized current into your normal metal. What means spin polarized current? As we discussed at the very first lecture, the ideal spin polarized current, it's when spin with one polarization moves in one direction and spin with opposite polarization moves in the opposite direction. So this is what you see here schematically. So spin pumping induces spin polarized current. And then imagine that instead of normal metal with small spin orbit interaction, for example, copper. Yes? If you have this metal copper, then you can make it 500 nanometers thick, and this spin polarized current will be reaching end. So it will be a good conductor for spin polarized current. But in most of the experiments, what we do is vice versa. We replace this material with something, this very large spin orbit interaction. For example, platinum, palladium, tungsten, and so on. And in this case, we will get large spin Hall angle, which means we will get pronounced spin Hall effect. And spin Hall effect, as we discussed already in the previous lecture, is in such effect that spin polarized current, so that direction in which electron will be scattered on some homogeneity depends on its spin polarization. So spin with one polarization will be preferably scattered in one direction, and spin with opposite polarization will be scattered in the opposite direction. And then if you have the situation that originally you have spin polarized current, so it means that spins with opposite spin polarizations are propagating already in opposite directions, then they will be scattered into the same direction. Yeah, so this is inverse spin Hall effect when we convert spin polarized current flowing here into charge current transfers to the spin polarized current. Yeah, so then, of course, in such case, you just excite magnetization precession, you will get spin pumping, spin polarized current, and at the end of the day, you will get inverse spin Hall voltage, which you can detect at these two contact paths. And yes, we discussed all these three vectors should be perpendicular one to another. So spin polarization, spin current polarization vector sigma is given by the magnetization, so it's pointed to us. The spin current always flows perpendicular to the interface, and charge current is perpendicular to these two voltages, these two vectors. This is the main idea, and with the last slides, I would like to show you just the simplest experiment which we performed quite some time ago to combine spin pumping and inverse spin Hall effect. It's really a very easy experiment. So what we did, we took, and therefore I just plug it in into the lecture to get a better understanding how it looks in reality. We just take yttrium iron garnet sample. So YIG is insulator, as we know from this course. Its material is very small spin wave damping, and its material where you can excite spin wave. So usually it's grown using lift-phase epitaxy on gallium gadolinium garnet substrate, which is thick, and YIG itself is, in this case it was 2 micron in this experiment, but it can go from 10 nanometer up to hundreds micron. The sizes of the sample is macroscopic, so principally we could make an experiment for students in this way. So this we used either 3 to 3 millimeter structure, or in some cases we use such waveguides when we wanted to excite also propagating waves. But this platinum covered here, this size is usually was 3 to 3 millimeter. It's large. And then on top of this, in a heat remark garnet, we just deposited platinum. Platinum is 10 nanometer thickness, 10 nanometer, because this is expected spin diffusion length of your material. And if you will make it too thin, then you will get a reflection of spin polarized current, and it will be sent back to your heat remark garnet. It will induce spin transit torque. If we want to avoid reflection, we don't want to make platinum very thin. If you make it very thick, then inverse pinhole voltage will work only 10 nanometer thickness, and the rest of platinum will work like a shortcut. So just it will be like you have battery, and then in addition you put additional conductors. Therefore, 10 nanometer seems to be optimal thickness for this experiment. It's very important to have interface proper here. In one of our papers, we have shown that even after standard cleaning procedure of your surface of heat remark garnet before deposition platinum with ultrasonic acid, so standard procedures, if you will do some additional in situ argon cleaning, or you will use some special chemical cleaning, you principally can change the efficiency of your effect more than 2 orders of magnitude. So this is a sample. And then you see here brilliant light scattering setup, laser beam. So it's not of importance for this lecture, but just keep in mind that principally you can use optical technique to get additional information what is going on in Magnonics system in your structure. But it's not of importance now. What is important is antenna. So we just use such antenna with characteristic impedance 50 ohm, which is used for magnetic resonance studies and so on. So just standard microstrip, and we send microwave pulse to excite magnetization precession. So it's an experiment in which we combine spin pumping, which starts with magnetization precession, and this inverse pinhole effect, which then give us at the end of a day voltage. Therefore, this voltage we can simply measure with oscilloscope here. Oscilloscope means usually it's not the most sensitive technique. This is a technique which gives the possibility to see something in time result, but usually you cannot measure nanovolts or something like this. And here, since this effect is so robust and so pronounced, we could just connect it to oscilloscope. And as we discussed, we need to make sure that 3 angles are parallel, so magnetic field polarization points in this direction, electric current, which we'll measure, points in this direction. That's why we connect it like that. And spin polarized current is always normal to the interface. So its geometry is right. And then how experiment looks like. As I said, we want to do it in a time result manner, because it gives us additional information how fast are these processes, what else to expect there. And this is what you see from your oscilloscope. So I on purpose just made a print screen from oscilloscope here to show it for presentations and lectures, because this is probably one of the most straightforward and simplest experiments I performed in my life, because it's absolutely robust and absolutely simple. And what you do in this experiment, we measure 2 signals. This pink signal, it's a microwave signal which goes through this microwave antenna. So it means that now we apply signal at 7 gigahertz. So this is pulse. We have here 500 nanosecond per division. So let's say 1 microsecond long pulse with 7 gigahertz carrying frequency, but we didn't apply magnetic field here. That means that everything with microwave pulse which was applied to this antenna just passes through, and this is maximum energy we see. So everything which was simply goes through the structure, and we measure it with this pink signal. So pay attention that here it's inverted, so especially done that you can better see it, but it's clear that you can invert polarity of your signal which is sent to oscilloscope. And green one, it's inverse pinhole voltage. So this is something which is detected directly here at the this contacts of platinum, and you see that there is no voltage. Okay, there are some parasitic signals, but this is just always happens when you have something fast changing in the system. So this is just parasitic response. Now what I do, I want to change field in a way that my ferromagnetic resonance frequency, the resonance frequency of excitation magnetization procession, will fit to 7 gigahertz. In this case, we had to apply field 175 millitesla, and in this case, we excite magnetization procession very efficiently, so it's maximum of excitation at 7 gigahertz. And what we see, that red signal became smaller, so it was like this, and now it's only small fraction of energy goes through the structure because most of applied microwave signal went into yttrium iron garnet, and all this energy was used to excite magnetization procession. And that's what we clearly see here. This is just a signature for us that now we really have a magnetization procession. And if you look now on voltage measured here, this green channel, you see that we have voltage. So it takes some hundreds nanoseconds, but this is related to the dynamic of spin waves. So you need, and magnetization procession, you need to excite magnetization procession sometime. Then after you switch off pulse, it still will take some time to dissipate, like we already know. But the main message is that you see here, we see voltage. And this voltage is 1.5 millivolt without any amplifier. That means that this is very robust, powerful effect. And of course, what you do always in this kind of experiments, you need to check if you really see inverse pinhole voltage or it's some parasitic effect. And in this case, we are very lucky because we have this rules that 3 vectors, magnetizations, spin current and charge current are always coupled with cross product. It means that if you will change now the direction of magnetic field, you should have a change in the sign of voltage. So it means that now if I will switch field direction, the electrons will start to accumulate on the other side. And in experiments, it's very easy to do. You just switch magnetization polarity, and you see that voltage changed the polarity also. The same, just another polarity. Transmitted signal, of course, didn't change because you still spend the same energy to excite the magnetization procession. So much about spin transit torque and spin pumping. I hope you got a general understanding what are these phenomena and how you can see them, how you can measure them in the lab. And we are ready to switch to spin caloritronics phenomena. Spin caloritronics, it's a field of science which deals with spin polarized currents created not by DC current, like we discussed in past, and not by RF signal, like we discussed in spin pumping, but by application of thermal gradient. So now we will learn how to convert temperature into spin polarized currents.